Okay, so around 30 plus people are here. So let us start with lecture 10. There's one more problem I want to discuss. It is a graphical problem, but we solve it using dynamic programming. So are you able to see the screen?
Yes, ma'am.
Yes, ma'am.
Okay. So the problem we have is known as a traveling salesman problem. So I don't know if you have heard of this problem. It is a problem of, sorry, there is a salesman who has to visit, let's say, some number of cities. He has to start from a particular city, visit all the cities exactly once, and come back to the starting point. So uh, this tour which he's going to take, starting let's say at what city number one, visiting all the cities and then coming back to one. There are different paths between these various cities. He has to select this tour in such a way that the length of the tour is minimum of all the possible combinations you can have. Okay. So there's something known as a Hamiltonian path, which is basically finding a Hamiltonian path in your graph is your traveling salesman problem. Okay. So you start at a city, to all the intermediate cities, and then come back to the city. So how do we find the shortest possible route? So when you start at one, you have, let's say, 10 cities in front of you that you have to visit. There are this 2 raised to power 10 subsets, but we are looking at the subset with all the 10 cities that you have to, uh, just a second, yeah, that you have to visit. So you can visit them in any order. And of all the orders, you have to find the order which has the least traveling cost. Okay, so let's go to so any possible, when you start at one, you can visit in any order and then come back to one. So which one will you select? Okay. First of all, what is there to if you're solving it using dynamic programming, what is there to minimize or optimize? We have to optimize the length of the tour. So the length of the tour has to be minimum. Okay. So for of all the possible paths that you can take between these cities, you have to find the path with the minimum cost or the lowest cost. So it's a minimization problem. And what are the for dynamic programming, we need to represent the problem in terms of subproblems of same size, of smaller size. So once a city is visited, you have remaining cities, and you need to again, so you are left with a set of cities which is one less than the original because you started at one. Let's say there are n number of cities. You when you're starting at one, you are left with n minus one cities. So you have to visit these n minus one cities and then come back to one. Okay. Just a second. Let me just. Okay. So once you visit a city, you are left with n minus one cities to visit, and then from the last one in this set, you will come back to one. Okay. Then suppose from these n minus one cities, you select a city X. Then you are left with n minus two cities, and you have to minimize the cost of that. So our sub problem is one less than the original problem. So that is regarding the sub problems. But what about the bottom up approach? How do we solve? It's a dynamic programming problem. Can't I see the waiting room here? Okay. It's a dynamic programming problem. And are you still able to see the shared screen?
No, ma'am.
No?
No, ma'am.
Now?
Yes, ma'am.
Okay. So, two things. What are our sub problems? Once we select a city, we are left with n minus 1 cities to find the shortest store. Then, how do we calculate in a bottom up method? For that, let's look at the next slide. So, if you start at 1, so for a given problem, you will be for a given problem, you will be given the starting point. So the traveling salesman starts at city number 1. Okay, let's say there are 4 cities in all. So what are the possibilities? From 1, you can either go to 2 or 3 or 4. So it is not like your Prim's algorithm finding a minimum spanning tree that you say, okay, from 1, 2 is the shortest distance, so let's go to 2, because that will not be an ideal solution, because maybe 3 onwards, if you had chosen 3 onwards, you had lesser distances between 3 and other remaining cities. So you cannot take the decision at the beginning only. You have to consider all the paths. It's not about the edge between 1 and 2 or the distance between city 1 and 2. It is about all the possible combination of paths. So if you look at this tree, I have made the last one as this as dotted here, just to show that from all these cities in the end you have to come back to 1. So you have to add that cost as well. Okay, so you can go from 1 to 2 to 3 to 4 and come back to 1. Okay, this is one path. Or you can go to 1 to 2 and then 4 and then 3 and then come back to 1. So this is another path. So if you see 1, 2, 3, 4, 5, we have 6 paths in 6 combinations. We have to find the path with the least cost. Now, wherever, how we do it in a bottom up approach, whichever whichever city you visited last, this is the last level. Okay, so you might take any of these 6 paths that are there. So you might take any of these 6 paths and you can end up in this level. If you see in this level, you end up on city number 4 twice, you end up on city number 2 twice, you end up on city number 3 twice. Okay, so one of the cities in the rest of the cities is going to be the city where you end, and from there you have to come back to 1. So if what I've written here on the right hand side, the cost of going from city 2 to 1, you see that 2 times. The cost of going from city 3 to 1, this one here, you see that 2 times. So this is a sub problem which is repeated at a lower level. So if I already know the cost of going back from city 2 to 1, I can have that cost put here. Let's say 4 to 1 is the distance is x. If this is calculated, next time when I need 4 to 1 here in this path, I can use this x and then add it to my cost. Okay, so we start at 1, we reach whatever the last node in this level, and then we go back to 1. So these are all the possible paths that are there. So how many different paths will be there? This tree will be bigger if there is one more, let's say a fifth city as well. So you'll have branches for that as well. You'll have that 5 here as well, right? So more combination, as the number of city grows, the number of paths possible will also grow. Okay, now first let's represent this in a mathematical form so that we can give some structure, give some recursive or a mathematical structure, and be able to calculate our problems in a bottom-up fashion. So what is given at hand is a graph. You'll be given a graph of the cities, and the edges of the graph will represent the distance between the cities. Okay. So if there is an edge, if there is a path between two cities, you will have an edge and that will have a weight. If there is no path, the distance will be infinity, and the distance between u and v cannot be negative because this problem does not you have graphs with negative weights which have some specific meaning. Here you cannot have a negative weight because you we are talking about distances, so there has to be some distance. So if we start at any city I, for example, so we start at I, we need to visit S cities and we have to return to I. So if you have a set of cities, if you have started at I, what you are left with is the set S minus the city I. These are the rest of the vertices. So out of all the vertices you had, you selected I as a starting point. So what you are left with to visit, like it said, there are n vertices, you select one vertex, n minus one vertices are left, and that n minus one is your S minus I. Okay. Okay. So suppose we start at one. Okay. And after visiting some cities, we are at some particular city. So there might be more cities to visit after that, and then you have to come back to one. Okay. So what we have to keep in mind is once we select a starting point and once we have visited some cities in order, in whatever order, we are not going to repeat the cities. City one visited is done. So you can remove it from the set of vertices that are, you can have two sets, one which is already visited and one which you have to visit. So let's first define a function. What we have to do here is what are we trying to calculate? We are trying to calculate a path of a tour. Sorry, the length of a tour. So we need to store that length somewhere. So length, or you can say the cost of the tour or the minimum cost. So if GIS is the cost of the overall minimum cost of visiting each city in the set given to us exactly once, starting at I and ending at 1. Okay, you start at I, you visit all the cities in X, S, and then come back at 1. So let's say you have started at I, you have gone to some, all the vertices till K. From K, you have to come back to, if K is the last vertex, you have to come back to I, if I is your starting point. Okay. Okay. So when we say that we will calculate this problem in a bottom up fashion, we assume that if we start at 1, okay, and we have no city to visit after that. So let me just see. Okay, I'll go back to the expression later. What I want you to say, to tell you, if this G2 and phi, according to our definition of G, I, and S. What was the definition of this? This is the minimum cost of the tour, which you start from I and go to the intermediate set of vertices S. and then you come back to your starting point. Let's say I can be any vertex at any point of time. Let's say 1 is our starting point. So this if this here S set, if the size of this set is 0, that means you were at I and you have nothing more to visit after this. So that means you have to come from I back to 1 straight away because there's no intermediate vertex left. Okay. That is what your G2 phi says. It says the cost of starting at 2, visiting all the vertices in here, which is 5, which is basically empty, and then coming back to 1. So what is the cost of coming from 2 back to 1? There is nothing intermediate to visit, so it is just the cost of traveling from city 2 to city 1. So this, if you see in the graph that I just showed you with all the paths, coming back from 2 to 1, since 1 is your starting point, this will be your last step in the actual tour. But this is the smallest problem we have. So when we are doing a bottom up calculation in the traveling salesman problem, we say, what if I was at 2 and I have nothing more to visit? The subset of intermediate cities, there is no intermediate city. I was at 2, there is no intermediate city. That means I have to get back to 1 straight away. So that will be my cost of C21. What if I do this for all the sub problems that can arise? Since I have 4 vertices at hand, what if I was at 3 and there is no intermediate vertex? So that means I am looking at going from 3 directly back to 1. What if I was at 4 and there is no intermediate vertex here, it's phi or null? Then it is straight away the cost of going from 4 to 1. So if you see here, okay, this S, we have to do the calculation. GIS is the shortest path from I, visiting all the vertices in S and coming back to 1. So all the vertices, they can be, if there are 10 vertices, you start at I, there will be 9 intermediate vertices which can be visited in any order. So all the orders we have to calculate. You'll see in calculating all those orders, as you saw in the graph, there'll be similar subproblems. So we will calculate the subproblems first. Okay. And that we do by starting at a subset of intermediate vertices of size 0. Then we say, okay, if there is one intermediate vertex, how would my tour vary? Okay, so we'll get back to the problem. So what you look here, if I have given you that your starting point is 1, so you have to find the cost. G is the function which determines the cost. You have to find the cost of going from 1, visiting all the intermediate vertices except for 1, because you started at 1, no vertex is repeated, and coming back to 1. Okay. Okay. So if we start at 1 and we end at k, how should we select our next vertex? So if you are at any point, your next vertex should be selected in this way. What does this say? It says if you are at I and you have this set left, this set can have any number of vertices. If you select the vertex k from this set to go, let's say there are 3 vertices in this set. So there'll be 3 values you can possibly select. So you have to select all the 3 values, and then you have to see which of the 3 values gives you the minimum cost. So if you see at this equation here, if you are at I and you select k, that means you have to add to your path the cost of going from I to k. Now, if you have selected k, your set had, for example, S size was 3. Now this S here will be 2. So you're still left with 2 vertices. So from k, you can go to either of the 2 and then so for this, either of the two should also be, you have to see which one of the two gives you the minimum cost. Okay, so this one also needs to be calculated. So just a second. So you see this equation, let me explain. Once we do the problem, this will be more clear. So if you have a subset S left to visit and you are at I, out of that subset you can select any k, any vertex to visit. If you selected k, you have to add the cost of going from I to k, and you are left with the same problem, the sub problem, where you start now. So you selected I to k. Now from k you have to go to, you have, let's say the vertices 1, I had 1 2 and 3 here for example. So k is 1, so 1 is already gone, but from k you have to see whether you should go from 2 to 3, which path you should take. So this 2 to 3, this is this sub problem here. This sub problem is again going from k to either 2 and then so on, or from k to 3 and so on. So which one of the two is minimum? Once you know that, you substitute that value here, and then you add this cost to that, then you find minimum of all the three k's. Okay, uh, we'll see that in a while, so it'll be more clear. So what this equation is, just understand, once you select a vertex k out of the intermediate vertices available to you in S, you have to add the cost from I to k, and then from k to running through all the rest of the intermediate vertices left and moving on. Okay, so you see this, every time you select a k, this S here gets reduced by 1. So your S size, if it was 3, the S size here is 2. So 3 is dependent on 2, 2 is the sub problem of 3, right? So I need to have this value calculated first before I can get this. So if this size was 2, this 2 will further depend when the size is 1. So I need to have G values calculated for subset of size 1. This here it's subset of size 2. Here it is subset of size 3. Okay, so I need to have the lower values calculated first before I can calculate the higher values. Okay, so if your starting point is 1, whenever you're doing a traveling salesman problem, TSP we call it, if you start at 1, you'll be given what is your starting point. It can be anything, 2 3 4, so you have to modify your equation accordingly. So if you are starting at 1, what is the cost of going from 1 to all the other intermediate vertices? V is the total number of vertices, you're subtracting 1. So if there were 10 vertices, now you're left with 9 vertices in this set. So what is the cost? You don't know, out of, if you have 9 vertices left, if you started at 1, which of the 9 you should select? There are 9 possible paths at this point when you're just looking at the first edge. So this k will range from 2 to whatever n. If it is 10, so 2 3 4 5 6 7 8 9 10. Out of all the values, you have to calculate what is the cost of going from 1 to this, whichever vertex you selected, and what is the cost of going from that vertex k to all the leftover vertex. So this, if this was 9, this will be 8 here, the size. So you need to have this right hand side calculated first before you can calculate this left hand side value here. So in general, when you are at I and you have to go through intermediate vertices S, you have to find the minimum of all these possible values of cost of going from I to J and cost of going from J through all the intermediate vertices except J. Okay. So let's take a problem and then see what we are talking about, what we were talking about. So this is a graph given to you. Uh, it's a directional graph, so you know when you have arrows in the graph, it means that there is a direction. You can go from, let's say, you can go from 1 to 2. If you see, you can go from 2 to 1 also. In this, there's an arrow in the backward direction. So every city, there are two edges between every city here, so that means you can go in both directions, and the length of the tour or the path between the cities need not be the same in both directions. So you see the difference here. So if you just have one edge, it is considered to be a bidirectional edge. So you can traverse it in either way. But when an arrow is given, you have to follow the arrow. You cannot go in the opposite direction of the arrow. Okay, so now we have a matrix with the all these values given. Okay, this is a problem. You are given this map with cities and their distances, and you start at 1, and you have to find the shortest path to visit 2, 3, and 4, and then come back to 1. Okay. So how do we start? We start with the smallest problem. So if bottom up, if we are at 2 and we have to come back to 1, we are at 2. So we know we have started at 1. We could have gone to 2, 3, or 4. There are three possibilities. But let's say we are at 2. This is the last point, and we don't have any other vertex left to visit. Then what is the cost of going from, if you apply the formula, this set, there is no k value here, the set is empty, so it is simply the cost of going from 2 back to 1. Okay, so if I go up here, so this is what we are calculating. We're calculating 2 to 1. So we assume we have reached 2, whatever the cost of going from 1 to 2. So what we are calculating, what is the cost of the tour starting at 2 with no intermediate vertices and going back to 1. Okay, so this is the cost C21, which is simply the weight of the edge from 2 to 1. Okay, what is the cost of going from 2 to 1 from this matrix? It is 5. Aman, can you figure out where the number is coming from?
डॉक्टर आपसे एक बात करना था ये वाइफ प्रेग्नेंट है ये गलती से हो गया ऑन हो गया गलती
Okay, so this is when your subset of intermediate vertices is 0. Okay, then when the size of your subset is 1. Okay, so you are at 3 and your subset basically, let's go back to here. Okay, so when you are at this level, there is no other intermediate vertex you can go to. Okay, but if you are at this level, there is one intermediate vertex that you can go to. Okay, and what are those intermediate vertices? If you look here, there again, obviously they're going to be 4, 3, and 2. 4, 3, and 2. Okay, when you are at this level, you can either, you are at 3. If you look at this chain here, change the color. If you are at 3, you can go to 4 and then 1, or if you are at 3, you can go to 2 and 1. Right, if you are at 3, you have two choices still. The size of the subset is 1. That subset could be either 2 or either 4. So if you look here, if 2 is left as an intermediate vertex, so you could be at 3 or you could be at 4. Okay, you could be at 3 or you could be at 4. Mhm. The size of the subset is 1, so we are considering only one element. So what if that intermediate vertex was 2? If that intermediate vertex was 2, 1 is already gone, you have started at 1, so 1 is visited. The intermediate vertex we are talking about is 2. So you could get to city number 2 from either city number 3 or city number 4. So if you are going from city number 2 to city number 3 to city number 2, what is the cost? The cost of going from city number 3 to city number 2, then the shortest distance from 2. So what is left? There's nothing left. This breaks down to going from 2 to 1. So this is your total cost, 18. What if 2 is your intermediate vertex and you were at 4? So these are all the possibilities we are calculating. So you go from 4 to 2, and then from 2 to, there is nothing left, no intermediate vertex left. So 4 to 2 and 2 to 1. So the cost is 13. So if this point is not clear, let me know. I will repeat it. Okay. So again, what if there was one intermediate set, one element left in the intermediate set? So when I say this is 0, means there's nothing, right? So that's clear. When I say this is 1, this 1 could be the vertex 2, it could be the vertex 3, it could be vertex 4. If it was the vertex 2, then I am talking of going from 3 to 2 or 4 to 2, and then further on from that. If I am talking of that the subset which is left, or intermediate vertices left, is 3, so I am talking of this part now. So 3 is the intermediate vertex. So you could go from 2 to 3, or you could go from 4 to 3. 4 to 3 as in the set which has 3. So once you go from 2 to 3, you are left with the function g, which calculates the cost from going from 3 to rest of the intermediate vertices, which is null, which means it is going from 3 to 1. So you add the cost of 2 to 3 and 3 to 1. So you get 15. So similarly, you could have been at 4, and then 3 could have been the intermediate vertex, and then this is your cost. Okay. There is another now third one. So you could have 4 as the intermediate vertex. You'll see that in the next slide. So if 4 was the size is 1, these are all the possibilities. The size of the subset is 1. These are all the possibilities. So if 4 is the intermediate vertex left, you could have gone from 2 to 4 or 3 to 4. So 2 to 4 means going from 2 to 4 and then going from 4 back to 1. 3 to 4 going from 4 back to 1. So that these are the costs. Since there is, for every starting point 2, there is only one choice here, so we don't find that minimum. Your k goes, if you look at the equation, your k goes from 2 to n, right? 2 to n. So if the number of vertices here is only 1, then you don't have choice for k. Okay, you just have one choice. So there is nothing like calculating minimum of the 2 or the 3. That will arise in the next scenario. So when the subset size is 1. So what when the subset size is 2? So what do we mean by subset size 2? That means you are left with 2 intermediate vertices. Now these 2 intermediate vertices could be, leaving out 1, it could be 2, 3, or it could be 3, 4, or it could be 2, 4, depending on where you are starting. Okay. If you are left with, see, what are the combinations? 2, 4, 2, 3, and 3, 4. So you are, when you say this set is of size 2, what you have 3 vertices. Okay, the set can be either 2, 3, or it can be 2, 4, or it can be 3, 4. This set subset is of size 2. What are the possible, given the intermediate vertices, what are the different possibilities of finding subsets of size 2? These are all the 3 options. So we will consider each of them one by one. Okay. So if there, what I'm considering first is the set 3, 4. If 3, 4 is left to visit, you are only left, the starting point left with you is only 2. So you can, what this statement tells you, you have to start at 2. You could either go to 3, which is this case here, I just underline, or you could go to 4. If you go to 3, your calculation will be cost of going from 2 to 3, which is what I have ticked, and the cost of going from 3 to the rest of the intermediate vertices, which is what is left once you are visiting 3, you're left with 4. So you're left with the subproblem G34. And if you decided to go to 4, then you have to add the cost of going from 2 to 4, and then the shortest path from 4, obviously back, it's actually back to 1 through 3, because now you selected 4, so you'll be left with 3. So you'll add, so the k values can be 3 and 4. So out of the two, you have to see which of these two, this and this, gives you the least cost. I have highlighted the least one as red. So going through 4 gives you the least cost of 25. Okay. So this is one of the possible subsets of size 2 when they act as intermediate nodes. What if the intermediate node set was 2 and 4? Then what is the left out vertex? That is 3. That means you could be at 3, and now you have a choice of going from 3 to 2 or 3 to 4. So if you see here, so if you, right now you are here, okay, you have the choice. There are two intermediate vertices, 3 and 4. You can go from 2 to 3, or you could go from 2 to 4. Okay, so there are two paths, and then 4 onwards to 1. So again, we have already calculated how to go from 4 to 1, uh, least cost. So we'll do the calculation. So if we are at 3 and we could visit either 2 or 4, which one gives us the least cost? We have calculated. If we are at 4 and we are left with 2 and 3 as intermediate vertices, which one gives us the least cost? That is there. Now, okay, we increase the size of our subset to 3. Okay, when we say size of subset is 3, you have started at 1, so we are left with 2, 3, and 4. So there's only one subset of size 3, because our problem has only 4 vertices. So when we take the entire subset, so we have to calculate the cost of going from 1 through this intermediate set of 2, 3, 4, and obviously back to 1. So what is, we can select this k can be 2, 3, or 4. If k is 2, we calculate C1 2. If k is 3, we add C1 3 and C1 4. And on the right hand side, you'll see if we have selected 2, then we are left with G of 2 and through 3, 4. The cost of going from 3 through the intermediate vertices 2 and 4. The cost of going from 4 through 2 or 3. So we have to see, we have already calculated the minimum of these. If you go back, we have already calculated G423, G424. So that is already done. So we use those values. This is where we are actually storing the smaller problem values and then adding them. Okay. So doing the calculations here, you get the minimum cost is 35. Now this is just the length of the smallest store, right? So just like in every problem, you find the value. This is the minimization problem that we had to do. So we have minimized to, we have calculated the minimum cost of the path of going from city 1 to all the other cities and coming back to city number 1. But what is the path actually and how can we find it? So we have to we have to trace the path back from our solution. So when you so I have highlighted where the least cost came from. This 35, it came from this one. Okay. What does that mean? That means when we were at 1, we have selected 2. Okay. We have selected the cost of going from 1 to 2. And then our problem was going from 2 through 3 and 4 back to 1. So let's go back up and see where did this G of 2, 3, 4 come from. So this is G of 2, 3, 4. So G of 2, 3, 4, it was minimum of, it was minimum of G of 2, 3, then 3, 4, or G of 2, 4. If you see, the minimum value comes from when you go from 2 to 4. Okay. And then we are left with the subproblem G of 4 through 3. So let's go back to our earlier problem and see where G of 4, 3 comes from. G of 4, 3 comes from, it is actually G of 4, 3 and then 3, 1. So let's go back here. So G of 4, 3 and then 3, 1. So this is our actual tour that we have taken to calculate this cost of 35. Just a 1, 2, 4, 3, 1. This is your optimal tour route. So just like in matrix multiplication, we have the K table, knapsack, we have the B table. In least common subsequence also, we have another table to store the values, which gives us the actual subsequence. Here, this is the actual cost comes from storing which K value gives you the minimum cost, because we are doing the calculations out of all the 3 possible K values here, which is 2, 3, and 4. So we have to store K is equal to 2 in this case. So which tells us that we went from 1 to 2. And then this part will give us from 2 we went to 4. And then from 4, obviously, it's 3 and 1. So in a way, we are calculating all the, we're first calculating, if you see the last equation that we calculated, it calculated the cost of this edge plus the cost of this. The cost of this and the paths, we had already minimized where this cost came from, whether it came from this one or it came from this one. So we have already found the minimum, and that we use that minimum here and add it with the cost of the edge, and then we find what is the least cost. Okay, so okay, what is the, I forgot to add that slide, the runtime and the program. So what do you think will be the runtime of this, of solving this problem? Of the order of what? How many calculations have we made in all? This is just a simple addition and minimization. Look at the tree. So we had three equations here to calculate the cost of going from 3 to 1, 2 to 1. Here we had 6 and 1, 2, 3, 4, 5, 6. I think here we had three calculations. So I actually forgot to add the, let me just make it last notes and see. Just a second. O(n) square, sure, 2 to the power n. N square to into 2 to the power n. No, it is 2 to the power n, but not uh, n square, because what we are, when we start at a particular vertex, okay, then we are looking at let's say n minus 1 vertices, and we're looking at all the possible uh, permutations and combinations of that. So I have to write it down on the whiteboard. So for each step, for each intermediate set that you're calculating, you have n minus 1 choices for I. Okay. So if we exclude your first vertex and your ith vertex, you are left with these many combinations, distinct sets of S. Okay. So your, if you find, so this comes up to n minus 1, 2 to the power n minus 2. Okay, I'll add that to the class notes. I forgot to add this because I I took the example from somewhere else. Just a second. Yeah. Okay, so uh, I'll add this explanation to your slides and then upload it. I think I have to upload the previous one also. So, any questions in this? There's one more graph example for dynamic programming. It's known as the Floyd-Warshall algorithm for finding the shortest path. It actually deals with calculation of matrix of values in a bottom-up fashion. So it gets very complicated to even do it on paper, but I think having a presentation would be easier. But I'll keep that on hold till we actually go into graphs and study about shortest path, length of the shortest path from a node to all the other nodes and other algorithms like that. And then if we have time, we'll go through that. For now, this will be the last topic of dynamic programming. What we'll take up after this is greedy algorithms. So I think we don't have a class tomorrow. In case I get time, I'll let you know in the morning if I'll take class or not. But I might have a meeting tomorrow, same time. And in case Aman, some one of your
Yes.
teachers shifts the class to afternoon or something, just let me know in advance, so I can.
Ma'am, actually, the whole slot is booked tomorrow.
Okay, tomorrow you don't have space in the morning, but
Yes,
generally they
ma'am.
say I asked the Hoor ma'am for today's slot. She said she had already shifted it. So in
Yes,
case
ma'am.
there is
She,
something like that, just let me know because it's
ma'am,
yeah.
actually, tomorrow, ma'am, we are having 2 hours class, extra class for DBMS, and
Mhm.
we might have one more class
Okay,
for
let's take on Monday. But
my.
just in case there is a free slot, let me know so I can take the class earlier,
Okay, ma'am.
and then you're also free for the day.
Okay, ma'am.
Okay.
I'll let you know.
So for tomorrow, let's not have class. So we'll have it on Monday then. Okay. I will also try to upload these lectures. Actually, I have been recording these Zoom lectures, but uh, you have to rename them and all that because they are not they are stored in a folder, so I have to go through all of them and name them lecture wise. So I'll do that and try and upload those by weekend. I have to upload last two lecture notes, and I might also give you an assignment this weekend, hopefully. Okay. uh, please take the attendance.
Yes, ma'am. I'm taking. Done, ma'am.
Okay, what somebody asked what input parameters we need for this problem. You'll be given basically just a graph. If you're given a graph with the cost of going from one city to another city, that's it. So you make the or you'll be given a matrix, 2D matrix, which gives you the cost of traveling from one city to another. So you have a set of vertices. The number of vertices you have will determine how big your problem solution will be. So that n is the number of vertices uh, in the graph, or the number of cities that you have. Okay, so because based on that, your intermediate set, like we had four cities, so the size of the intermediate set was 0, 1, 2. So if you have five cities, you'll have another step where size intermediate size the size of S intermediate nodes will be 4. Then you'll have four options there to minimize four paths. So it will grow. Only connected, obviously. If it is a disconnected graph, then obviously you cannot go to that city. It's supposed to be a connected graph where all the cities are connected in some direction. It might necessarily not be bi-directional connections, but there has to be a path, otherwise you cannot solve this problem. Okay, any other questions? All right, thank you.